Welcome to the next lecture, and in this lecture we'll be learning about indices. Now, what typically is an index? It is something which looks like this, wherein you have a base and the power here is called as a index. So indices are basically any constant raised to another constant. Yeah, this might be a variable also, but that will deal when we start doing functions. So as of now, indices are species which have a base and a power. As of now, we'll keep them integral. So like for example 2 cube, the motivation comes from here. 2 cube is nothing but 2 into 2 into 2. Then 2 raised to 4 is 2 into 2 into 2 into 2. So there are 4 2's multiplied is nothing but 2 raised to 4. There are 3 2's multiplied, hence it is 2 raised to 3. If you remember, addition like adding 2 thrice is nothing but 2 into 3. Adding 2 4 times is equal to 2 into 4. So in this way, we can see that 4 2's added gives us 2 4's are sort of. Yeah. So since multiplication is a simplification or simple way of writing multiple addition of a specific kind, we say that indices are nothing but multiplying a particular number that many times is easily presented in form of an index. So we are trying to generate some formulas when multiplication is done for a particular number again and again. Yeah. So like if I say a raised to m, let us take this as a definition of our discussion. So what is our definition? Let me get this whole motivation out. So the definition of an index is a raised to m is defined as a into a into a into and so on m times. So if you have this, you can write that. If you have this, you can write this. Yeah. So let us take this definition and try to derive some properties. So as of now, what I am having is I am having a bag full of numbers which are of this kind, and I am trying to define what all properties or operations I can define on them. So if I have a raised to m and I multiply it with a raised to n, then typically I have m a's, which is a into and so on. These are m a's multiplied by a into and so on. These are n a's. So typically if I simplify this, I see that in all, if I combine both these brackets, I have m plus n a's. By using this definition, I can write this as a raised to m plus n, and hence this first property is what we get. So here we are trying to list down all the properties of indices. Second property is a raised to m upon a raised to n. So here we are talking about product of indices. Here we are talking about division of indices. So here imagine I have m a's and below I have n a's. Assume without loss of generality that m is greater than n. Then what will happen? This a raised to n a's below will get cancelled. Like if I just show you this, imagine these a's are more in number and these a's are lesser in number. So what I can do, I can cancel each of these a's with the a's which are there here. So whatever are left uncancelled are nothing but m minus 1 a's. This can be written as a raised to m minus n. Yeah. So here we get the division property. Now from this property we get far more specific properties like a raised to 0 is 1. How do we get this particular property which keeps on coming again and again? So a raised to 0 is 1 is what we need to remember. So it is very obvious. Put m is equal to n in property number 2. So here if I put m is equal to n, so I get a raised to m upon a raised to m is equal to a raised to m minus m. This is a raised to 0, which is equal to 1. By this both being same, I get this as 1, and here I get m minus m, which is a raised to 0. So that implies that a raised to 0 is equal to 1. Fine. So please have a look at this property. Then there is another property which is a specific case of this particular second property. It is 1 upon a raised to n is equal to a raised to minus n. And this property says put m is equal to 0. If you put m is equal to 0, then you get this particular property. Yeah, if you get m equal to 0, you get this particular property. Fair enough. Now let us proceed in this direction with rest of the properties. If you have taken this down, I can move on to the next property. So I hope you got the basic idea of why these properties are true. So let me list them down on the right hand side as and when we are proving them. So the first property we saw was a raised to m plus n is equal to a raised to m into a raised to n. Second property was a raised to m upon a raised to n is equal to a raised to m minus n. Then third property was, rather they were the special properties of the previous one. A raised to 0 is 1, and second property was 1 by a raised to m is equal to a raised to minus m. Third property is what we will see. Now here we have seen the base is same and the powers are different. What if the base is different and the powers are same, like ab raised to m? This is nothing but a raised to m into b raised to m. So the power actually distributes over the bases, like ab raised to m can be shown as ab into and so on. How many ab's multiplied together? They are m ab's multiplied together. So we just take m a's together into m b's together, separating the pairs. I get a raised to m into b raised to m. Hence this property. Similarly, we can say that a by b raised to m is equal to a raised to m upon b raised to m. So this is also not different. A by b raised to m is nothing but a by b into a by b and so on into a by b. How many a by b's multiplied? M. So I just take the numerator separately. How many a's? These are m a's. And how many b's here? They are also m b's. So I get a raised to m upon b raised to m. Yeah. The next property is, which actually comes something like this. It is a raised to m raised to n is a raised to mn. If I try to prove this property, it's not very difficult to prove. You can pause the video if you want to understand something in between. So a raised to m raised to n is nothing but a raised to m into a raised to m and so on a raised to m. How many such a raised to m? N. And now each a can be opened up. How many a's are there? M here, each of them into a into a into a. How many a's? M and so on a into and so on. How many a's? M. And how many such brackets are there here? N. So I get this is a raised to mn, because now in all how many a's will be there? Each bracket has m a's. Total number of brackets is n. So mn a's are there. This is how we get it. And this can also be written as a raised to n raised to m, if you try to check this. So this is also equal to a raised to n raised to m. So these powers can be interchanged. Yeah. Now we can see that each bracket has n a's and number of brackets is m. That is what this signifies. Okay. Shall we go further? Now we'll start solving some of the problems. If you want to see, you can have a look at the properties on the next page listed. So these are one by one properties. Okay, let us take this problem. This is one more important theorem which we have to discuss. Now try this problem, please. I am pausing. I pause this video for some time. You can pause it and try this problem. Okay, I hope you're done with trying this problem. So let us solve this problem. The problem at hand is x minus 1 raised to x is equal to x minus 1 raised to 4. Now the obvious answer most of you might have got is base is same here, so powers have to be same. So the solution is yes, x equals 4. That's correct. But there are other solutions also. What are the other solutions? These two powers might be equal, rather this raised to this, x minus 1 raised to x and x minus 1 raised to 4, they might be equal because x minus 1 is equal to 0. This is one of the possibilities. If x minus 1, that is this denominator, this base, if it becomes 0, then 0 raised to anything is what? 0, except when the power is 0. Okay, so this we can take as a note here, as a concept. Let me discuss this as a concept. Concept number, maybe we can start this as concept number 1 in indices. So the concept is, it says a raised to 0 is 1 only when a is not equal to 0. Therefore 0 raised to 0 is undefined. That's why we are not allowing it. Yeah, so this is a very important concept. 0 raised to 0 is undefined. Okay, so we need to make sure that we don't get 0 raised to 0 here. So if x minus 1 is 0, that means x will be equal to 1. That means the power here is 1. So what kind of a structure we have? 0 raised to 1 is equal to 0 raised to 4. And does it satisfy? Is it true? Yes, it is true. 0 raised to 1 is equal to 0 and 0 raised to 4 is also 0. Hence x equal to 1 is also the solution. Yeah. Then what are the other possibilities? X minus 1, that is a base. X minus 1, that is a base. This base can become equal to what? This base can become equal to 1. So if x is equal to, x minus 1 is equal to 1, that means x will be equal to 2. So if you put x equal to 2, what do you get here? 1 raised to 2 equals 1 raised to 4. Yeah. So this also works fine. Therefore, what do I have? X equals 2 is also a solution. This also is a solution. So this also was a solution. X equal to 1, x equal to 2 also. Now let us try another thing. Let us put x minus 1 is equal to minus 1. If the base is minus 1, so I get minus 1 raised to minus 1. Rather, if x minus 1 is equal to 1, that means x will be equal to 0. So put, I get 0 raised to minus 1 is equal to 0 raised to 4. Or that I think we have already calculated. If I put x is equal to 0, that means I'll get here minus 1 raised to 0 is equal to minus 1 raised to 4. Is this also satisfying? Yes, it is satisfying. Hence x equal to 0 is also a solution. So in all, how many solutions we got? X equal to 0, x equal to 1, x equal to 2 and x equal to 4. So there are total 4 solutions to this problem. So the correct answer is going to be this. So you have to take this answer. So why we actually took all these cases, like base can be equal to 0, base can be equal to 1, base can be equal to minus 1, or base can be anything other than these three numbers. This turns out to be a new theorem, which we'll see in the next page rather. Just copy this down. I'll give you some time to copy the concept, to copy this particular concept as well as this particular solution. Pause the video. Pause the video. Okay, let us move further. So this is the theorem. In the next page we have the theorem says if a raised to m is equal to a raised to n, then if a raised to m is equal to a raised to n, then there are many possibilities. M can be equal to n, that the powers will be equal, which was the obvious conclusion, or the base can be equal to 1. 1 raised to anything is 1. So this equation has to satisfy. Or what can happen? A can be equal to 0 except m n not equal to 0. This m and n should not be equal to 0. Other than that, this should be fine if a is equal to 0. And then the next value is a is equal to minus 1. So in this case, m n has same parity. So if a is equal to minus 1 and m and n have the same parity, then we say that these two are going to be equal. Yeah, so you have to be very careful. So if a raised to m is equal to a raised to n, then these are the 4 conclusions which take place, not just this single one. Yeah, so I can just show you quickly what do you mean by same parity. So this particular will take as a concept parity. So if m n have same parity, means both are even or both are odd. That is what we mean by the word same parity. Yeah, same parity. What do you mean by opposite parity? Means m and n, if they are having opposite parity, that means m and n, if m is odd then n is even, if m is even then n is odd. That is what we mean by that. Okay, so this becomes very important. So this theorem is very important. That is what we have used in the previous problem. Now let us come to this problem. This will come as a separate note which we have already listed. Concept number 3. Whenever there is exponential like a raised to b raised to c raised to d, we have seen that it will resolve like this: a, b raised to c raised to d. So c raised to d will get resolved first, then b will be raised to that number, and then a. Like for example, 2 raised to 2 raised to 3 raised to 2, if I have, this will become 2 raised to 2 raised to 3 raised to 2. It will work like this. So it will become 2 raised to, this will become 2 raised to 3 square is 9. It will be something like that, and 2 raised to 9 is whatever, I think it is 512. So it is 2 raised to 512. Let's not calculate after this. So this is the next concept. Now if I want to simplify this problem, let me take the first one, 2 raised to 3 raised to 2, this will become 2 raised to 9. Second one is 2 raised to 3 square, here we have bracketed it, so it is again 2 raised to 9, so a and c are equal. The third one, 2 raised to 3 raised to 2, is nothing but 8 square, so therefore that's obvious that a is equal to, a option is equal to b option, and this option is more than c option. This is what we have concluded. Okay, so this note is very important when you resolve powers or rather exponentiation. Now please try this problem. I'll give you some time. So prove that 1 upon p plus q raised to minus 1 plus 1 upon 1 plus q plus r raised to minus 1 plus 1 upon r 1 plus r plus p raised to minus 1 equals 1 if pqr is equal to 1. So I just pause for some time. You can pause the video. Okay, now let me solve this problem. Just check whether you have solved it. We have to show that this expression, this complete expression is equal to 1. And when? So basically, I think the most number of problems which are not solved completely is because we don't give importance to whatever is given in the problem. So what is given for us in solving this problem? That PQR is equal to 1. This is given. So we need to use it in the solution of the problem. So given is PQR is equal to 1, that is given. Now let us take the left hand side. Now what I do, I call each of these terms, like this term I call as 1, this term I call as 3, and this term I call as 2. So let me first solve the first term. Let us simplify the first term. 1 upon 1 plus p plus q raised to minus 1. Let us try to simplify this using this given information. Okay. So what I do, I try to multiply, because there is q raised to minus 1. What is q raised to minus 1? Okay. Before we proceed into this problem, let us see some specific examples, special cases of all the powers which will keep on coming again and again in our problem solving. So special cases. So first is say a raised to minus 1 is 1 by a raised to minus 2 is 1 by a square. This is that property which a raised to minus m is equal to 1 by a raised to m. Then third is a raised to half is equal to square root of a. Fourth one, a raised to 1 by 3 is cube root of a. This is radical way of writing it. Fifth is a raised to 2 by 3 is a square and then cube root of a square. Sixth one, a raised to minus half. A raised to minus half is 1 by a raised to half, which is nothing but 1 by square root of a. Yeah, so I hope these things are clear. These are some specific examples which will keep on coming again and again. So if I write seventh property a raised to p by q, that means it is a raised to p and then qth root of a raised to p. Yeah, so whatever denominator we have over the power, it always goes in creating the square root, or rather the root. Yeah, so coming back to this problem, I don't like this term q raised to minus 1. So what I do, I multiply above and below by q so that it vanishes. So q multiplied above and q multiplied below. This is what I am trying to do. Yeah, so q multiplied above and below, I will get q plus pq plus 1. This is what I get. Now since pq is given, can I write pq as 1 by r, or rather r raised to minus 1? Can I write that? Because pqr is equal to 1. It comes from here. That's fine. So from here I write this is nothing but q plus r raised to minus 1 plus 1. But you will say that we actually removed q raised to minus 1, and why are we getting r raised to minus 1? It is because I observe that this expression is same as this expression in the second term. Can you see 1 plus q plus r raised to minus 1, which is lying here. Yeah, so this is what I call is coming from 1. Okay, and what we are seeing is, see, when now just understand the crux of this whole discussion. The crux of this whole discussion is this complete term added gives us 1. That means whenever you are adding 3 fractions, you try to make the denominator same. So what I am trying to do is this denominator equal to this denominator, I'll just make, and then this denominator also I'll make equal, and then add the numerators here. That is what I'm trying to do here. Okay, so let us go further. Now the second term, I'll keep it as it is. The second term, it is nothing but 1 upon 1 plus q plus r raised to minus 1. I'll keep it as 1 plus q plus r raised to minus 1, because the denominators here and here are same, so that I can add them directly. Okay, now let me come to the third term here. Third term is 1 upon 1 plus r plus p raised to minus 1. So what I do here, obvious thing is, I want to make this denominator equal to this denominator. correct? So I just try something. I try to remove this p raised to minus 1 by multiplying p above and below. So if I multiply p above and p below and then just multiply, I am not showing it here. So when I multiply, I get this is p, p into 1 is p, p into r is pr, plus p into p raised to minus 1 is 1. P into p raised to minus 1 is 1. So once I get this, I see that this denominator is not same as this denominator. It has changed. Rather, this will become, like for example, if I simplify it more, I write this as p, this will become p, and pr will be equal to q raised to minus 1. Just like this, pr will be q raised to minus 1. pr will be q raised to minus 1. Okay. So that is something which I don't want to do. So what I get here is p plus q raised to minus 1 plus 1, which is not same as the denominator here, here or here maybe, which we want to sum up. That's not happening. So our strategy of multiplying p raised to minus 1 is not correct. That is what we are observing. Yeah. So we'll just get rid of this part and we'll try to think something fresh. Now just observe this first term and the second term, they do have the same denominators here. You can see this denominator is equal to this denominator. So this will get added with this q. So if I add, I will just show you. If I add 1 plus 2 equation, I will get q plus 1, that is numerators get added here, and the denominator is 1 plus q plus r raised to minus 1. And what is the last term left out? This is the last term which is left out. Correct? And that will be, if imagine that last term ka denominator also, if we are able to make it 1 plus q raised to r minus 1, and whatever comes here, this two get added to give us 1. That means this term here should be same as r raised to minus 1. Do you agree? Because when you have r raised to minus 1 here, we will add this as q plus 1 plus r raised to minus 1, and denominator is also same, q plus 1 plus r raised to minus 1, they cancel and give us the 1. This 1 is nothing but what we require here. Correct? So obviously the term here in the third term numerator should be r raised to minus 1. Just think. So what I do is I deliberately create that r raised to minus 1 in the third term. Yeah. So in the third term, what I do is I have 1 upon 1 plus r plus p raised to minus 1. I multiply by r raised to minus 1 above and below to get r raised to minus 1 here, and below it will become r raised to minus 1 plus 1 plus pr raised to minus 1, because it is r raised to minus 1 into p raised to minus 1 into r raised to minus 1. I can take pr raised to minus 1 with the property. Correct? So this will become r raised to minus 1 upon 1 plus r raised to minus 1, and pr here is nothing but q raised to minus 1. So q raised to minus 1 raised to minus 1, that will become q. So again this is r raised to minus 1, 1 plus r raised to minus 1 plus q. So now what is happening? Can you just visualize here what is happening? I'll just get these special cases out. Can you understand what is happening here? From this is 3. So I get the denominators of all these 3. That is the left hand side. The left hand side is becoming 1 plus 2 plus 3, which is equal to q upon q plus r raised to minus 1 plus 1 plus 1 upon q plus r raised to minus 1 plus 1 plus the last one is r raised to minus 1 raised to 1 plus r raised to minus 1 plus q. So this denominator is same, so I just add the numerators q plus 1 plus r raised to minus 1 upon q plus r raised to 1 plus 1, that is equal to 1, which is equal to right hand side. So I have been proved. So hence proved is what we write here. Yeah. So I hope this problem is clear, the proof is clear. Just have a look at it and please copy this down. In the meantime, I'll put this slide on pause. So please pause the video and copy this down. let's move on. And let us discuss some more problems from the booklet. Let us take first problem as simplify the following expressions: x raised to half plus x raised to minus half upon 1 minus x plus 1 minus x raised to minus half upon 1 plus square root of x. You have to simplify this. So please try this problem. I'll put this on pause. You have to simplify this using laws of indices. Okay, let me solve this problem. So this step will become, what I do is, you need to learn what it means by keeping the solution clean. So always make sure that you write specific stuff. Don't try to do a lot of calculations on the solution, step. Either do the calculation mentally or on a rough page and then write things here, so that things become very, very clean. These powers actually don't keep the solution very clean, hence I try to convert them into radicals. So x raised to half is nothing but square root of x. X raised to minus half will become 1 upon square root of x, and I get 1 minus x plus, I'll get here 1 minus 1 upon square root of x upon 1 plus square root of x. The next step will be cross multiply. You get x plus 1 upon square root of x into 1 minus x. Remember this thing. Another note: a by b upon c will become a upon bc. This b will come down, and if it is a divided by b by c, then c will come up. This c will go up. Yeah. So just make a note of these simplifications if you are not aware of. It's always wise. Don't keep thinking about it. So what is happening here? Numerator created, cross multiplication created x plus 1 upon root x, and that root x came down, plus, if I cross multiply, I'll get root of x minus 1 upon square root of x 1 plus square root of x. So I've just done cross multiplication, and I have used the simple division multiplication. So the next step would be, now if you see here, I have root x here, I have a square root of x here, I have 1 minus x here, I have 1 plus square root of x. So if I want to add two ratios, then what is the rule of thumb? Denominator should be same. So what I do is, in order to make the denominator same, I see that 1 plus root x when multiplied by 1 minus root x above and below will get me 1 minus x here. This will become 1 minus x. So that will be my next step. That comes out to be 1 plus x here, root x 1 minus x, plus this will become minus 1 minus square root of x the whole square upon root x into 1 minus x. So you can see that this root x minus 1 into 1 minus root x, I can just take minus sign out of this here, and I can write 1 minus root x the whole square, because these two are same, just different by a sign. And then the next thing will be, I make the denominator same, 1 plus x minus 1 minus 2 square root of x plus x divided by square root of x into 1 minus x. Now what happens is, now whenever you are subtracting two terms, just try to collect similar terms together. So there is a number 1 here, I have a number 1 here, so 1 minus 1 will become 0, that is cancelled. Then I have x here, and we have an x here also, so it is x minus x, so it also cancels up. So whatever is left is root x, that is minus plus 2 square root of x divided by square root of x into 1 minus x. So this square root of x cancels, you get the answer as 2 upon 1 minus x. So this is the final value of this particular expression. Yeah, I hope everybody gets that answer. Now we pause it for you to copy this solution. Please copy this. Let us now proceed to the next problem. Let's take the next problem. Just get this out. So can you see the solution which I have written here is very clean? Let us come to the next problem, that is problem B, and the problem says simplify a minus a raised to minus 2, a raised to half minus a raised to minus half, minus 2 upon a raised to 3 by 2, minus 1 minus a raised to minus 2 upon a raised to half plus a raised to minus half. So please start solving this. I am putting this on pause so that you can solve it. Please pause the video and try this problem. Again I repeat, a raised to a minus a raised to minus 2 upon a raised to half minus a raised to minus half, minus 2 upon a raised to 3 by 2, minus 1 minus a raised to minus 2 upon a raised to half plus a raised to minus half. So let us, I put it on pause, please solve it. Okay, let me solve this problem. So the solution goes like, again I try to keep the solution very clean. Keep a clean solution. So let me show you again what is clean solution. A raised to minus 2 will become 1 by a square upon square root of a minus 1 upon square root of a minus 2 upon a square root of a. Now just observe here, a raised to 3 by 2 is a cube the whole square root, that is nothing but square root of a into a, correct? Or you can see this as a raised to 3 by 2 is nothing but square root of a the whole cube, that is square root of a into square root of a into square root of a. I can combine these two to form a, and this will be square root of a. So it is nothing but a square root of a. So I am trying to keep things in radicals so that the solution becomes very simple. Next step is 1 minus 1 by a square upon square root of a plus 1 upon square root of a. So I think this is a very simplified form. Let us now simplify the problem. This will become a cube minus 1 upon a square. This a square comes down, this a square comes down, into, I cross multiply things here also, it will become a minus 1 upon square root of a minus 2 upon a into square root of a minus a square minus 1 upon a square. This a square comes down into a plus 1 upon square root of a. I hope this is very clear. Let's take it for simplification. Now what I see is I can get rid of this using this property. We already know a minus b, rather a cube minus b cube is equal to a minus b into a square plus ab plus b square, and therefore I can say a cube minus 1 is a minus 1 into a square plus a plus 1. Okay, it's very clear. Fine. So using this I can just simplify this. I can write this as a minus 1 into a square plus a plus 1 upon this a square and square root of a will cancel to give me a square root of a, and a minus 1 minus 2 upon a root of a minus a minus 1 into a plus 1 upon a root of a, again the same thing, a square divided by a square divided by a square is nothing but a into root a upon root a upon root a. This root a cancels and we get a root a. That's what I'm explaining this particular part. Yeah. So once we get this, now we can, now we are free to cancel stuff. We can cancel this too. We can cancel. I'm sorry, I just forgot to write this a plus 1 here. It's an a plus 1 which is there here. So now we can cancel this too also, and the next step will come out to be equal to, next step will be a square plus a plus 1 upon a square root of a minus 2 upon a root of a minus a minus 1 upon a root of a. Now what do you do? Again, don't try to you can see the denominators are same all the three places. Now collect them together in one place, a root of a, and then see what happens. First of all, let us collect a square terms. A square term is here, there is no other a square term here, so I just write a square here. Collect a term, a, and there is one a here, so a minus a will become 0, so a does not come, so it is 0a, or rather I will just write 0. What about constants? 1 minus 2 is minus 1, minus 1 minus minus plus 1, that is also 0. So finally we get a square upon a root of a, that is nothing but square root of a. So this is the final value of this expression. So this whole expression when simplified is nothing but square root of a. Yeah. So I gave you some time. Please pause the video so that you can copy the solution. I pause the video. Okay, let me go to the next problem in this simplification. Let us take the third problem. C problem. The problem is x plus square root of x square minus 1 the whole square plus x plus square root of x square minus 1 the whole raised to minus 2 plus 2 times 1 minus 2x square. Find the value of this expression, or rather simplify this. What is this expression? So first time when you observe this particular term, you can see that this term is same as this term, both terms are same, just here the power is 2 and here it is minus 2. So what we are doing right now is observing the problem, and there is some term like 2 into 1 minus 2x square. This doesn't seem much related, but these two terms are of prime importance for us in our solution. So we have to be very much observant to what exactly, why these expressions are given and why one place there is power 2, other place there is power minus 2. Yeah. So if you keep observing, I see that, I mean this comes from experience, I see that x plus square root of x square minus 1, this expression multiplied by x minus square root of x square minus 1. Now this term and this term are conjugates of each other. Do you remember when you used to rationalize, like for example in school they used to ask rationalize this. So what you used to do? You used to multiply root 3 plus 2 above and below with 2 minus root 3. Correct? Let me simplify this problem. I am asking you what is the rationalized form of 2 plus root 3. What you used to do in school? You used to multiply above and below with 2 minus root 3. Correct? To get this as 4 minus 3 upon 2 minus root 3. This kind of expression you have to use to create. Correct? So what made me think this observation was because I saw that this part is fine but this part seems to be irrational. So why not rationalize this by multiplying by its conjugate? Let us see what exactly comes. So when I just see this is of the form a plus b, a minus b. So it's coming in the form of a plus b into a minus b. Yeah, this form which is a square minus b square. Yeah. So when this form comes, let me see what simplification takes place. I get x square minus a square minus b square, that is x square minus 1 the whole square. This comes out to be x square minus 1, that comes out to be 1. Okay, so I just see this is very strange observation that this particular expression into its conjugate is equal to 1. Yeah, so I'll just make a note of this particular observation here, that so let us write this separately as a very important property, x plus square root of x square minus 1 into its conjugate x minus square root of x square minus 1 is equal to 1. This is a very important property which will keep on coming again and again. So this is our observation, that this comes out to be equal to 1. Yeah. So now what I do is, just observe the way I play with this problem. What I do is, I write the expression as x plus square root of x square minus 1 the whole square plus, now this part I replace by this particular part. So what it comes out to be, 1 upon x plus square root of, rather x minus square root of x square minus 1 the whole raised to minus 2 plus 2 times 1 minus 2 x square. This okay? So what I have done is, I have rather replaced this x plus square root of x square minus 1 with this taken on the other side of 1 here in the denominator. Okay, so I hope you are understanding this. Okay, now let us proceed further. Next step would be, I just write this as x plus root of x square minus 1 the whole square, and this here we can use this property, a raised to minus m is 1 by a raised to m. So 1 by a raised to m, I can take this above as x minus square root of x square minus 1 the whole raised to minus 1 and the whole the power minus 2. This power is here, and when I take the reciprocal above, that is 1 by a, I am writing 1 by a as a raised to minus 1. This is what I am writing here. Okay, plus 2 times 1 minus 2 x square. So this gets me x plus square root of x square minus 1 the whole square plus x minus square root of x square minus 1 the whole raised to 2 plus, because minus 1 into minus 2 will become 2, plus 2 times 1 minus 2 x square. Now you can just observe this particular step, this much part is exactly same like as if we are asking what is a plus b the whole square plus a minus b the whole square. A plus b the whole square, middle term is 2ab, and here middle term is 2ab, that is minus 2ab with a minus. This is the middle term will get cancelled, and I'll have 2 times a square plus b square. Just observe, a square and a square from here will add up to give you 2a square, b square, and b square will add up to give 2b square. Middle term is 2ab, middle term is minus 2ab, give us 2 times a square plus b square. Okay, so if I add this 2, I'll get the next step as 2 times x square plus square root of x square minus 1 the whole square plus 2 times 1 minus 2 x square. So this boils down to 2 times x square plus x square minus 1 plus 2 times 1 minus 2 x square. Now just correct the terms. How many x square are there here? 2x square into 2, that will become 4x square, and here we are getting 2 into minus 2x square, that is minus 4x square, that becomes 0x square. Constant terms, 2 into minus 1 is minus 2, 2 into 1 is 2, added we get 0. So in all the expression value is 0. So this is the final answer. Yeah, just go through the solution and see if you have understood everything. Take some time, understand. I am putting this on pause the video and try to understand what steps we have gone through. Let us go to the next problem. Let us take and try to learn another technique in problem solving, and this is problem 3 in classwork problems. So if 5 raised to x is equal to 3 raised to y is equal to 45 raised to z, then prove that 1 by z is equal to 1 by x plus 2 by y. This is what we have to prove. So just comparing 5 raised to x is equal to 3 raised to y will not help us to come something like this. Now let us observe where we want to reach. This is given to us and we want to reach here. Now just observe, this given contains 5, 3, 45, x, y and z, but the prove that part does not contain 5, 3, 45, it only contains x, y, z. So the obvious method of solving this problem, or the strategy would be remove or get rid of 5, 3 and 45. That is, eliminate 5, 3 and 45 from the problem or from the given. Yeah, so this should be it's basically an elimination problem. So what I do is, I give you a technique. Whenever equalities are given, let this each of equalities be 5 raised to x equals 3 raised to y equals 45 raised to z equals some k. If this is equal to k, what is the value of 5? Just simplifying this, 5 raised to x is equal to k. Then what we do? We raise both sides with 1 by x because we want to find the value of 5. So I raise both sides with the power 1 by x. This will become k raised to 1 by x. Raise both sides to 1 by x. So this x would get cancelled and I'll get 5 is equal to k raised to 1 by x. So that is what happens here. This implies 5 is equal to k raised to 1 by x, 3 is equal to k raised to 1 by y, and 45 is equal to k raised to 1 by z. Now I want to eliminate 5, 3 and 45. So what I do? I create a relation between 5, 3 and 45. I know 45 is equal to 5 into 9, that is 3 square. Yeah, I will say we know. I hope we know. So 45 is nothing but k raised to 1 by z. 5 is nothing but k raised to 1 by x. And 3 is nothing but k raised to 1 by y the whole square. Yeah. So let me end this problem solution. So what I do from this step, I take it here and write this as k raised to 1 by z is equal to k raised to 1 by x into k raised to 2 by y. So by laws of indices, I can write this as 1 by x plus 2 by y, and outside I'll have k raised to 1 by z. So this implies 1 by z is equal to 1 by x plus 2 by y. Hence proved. So are you following how we approach this solution? It was first elimination, that is eliminate 5, 3, 45. So observation becomes very crucial. First step was to remove 5, 3 and 45 from the problem, and that was done by this relationship. Yeah, so I am putting this problem on pause. You may copy the solution and understand also. First understand and then please copy. Now take down some homework problems. Homework problems. Objectives. Page 5. Problem 1, 2, 3, 4 and 5. They are based on whatever we have discussed today. We'll get the solution for this in the next class. Then also try homework exercises. That is page 5. Homework exercise 1.1.1.2. Solve all of them, wherein first part is fill in the blanks. This is the first part. Second part is simplify. Just solve them, all of them. Now let us move on to the next topic, which is called as ratio. Let us work on that. So ratio is a comparison of two or more quantities in integral terms. Like for example, if I have mangoes which is say 10 in number and I have apples which are like 4 in number. So if I want to compare what is the ratio of apples to mangoes, how many number of apples is equal to how many number of mangoes in terms of their number, then I will write this as 4 is to 10 And if I write this in simplest form, this will come out to be 2:5. So typically, if I have A is to M is equal to 4:10, there is another representation which is division representation, which will tell me that A by 4 is equal to M by 10. So 4 apples and 10 mangoes, which can also be written, some people write this as A by M. I mean, take this M here and take this 4 here, they will write this as A by M. A by M is equal to 4 by 10. Then they write this as division form, simplify it and write this as 2:5. So A is to M is equal to 2:5. That is another way of writing. Yeah, but somehow I don't agree with that way of writing. So whenever I have, say for example, let us go to the next. I hope this is very clear. Let us go to the example. Say there are two objects X and Y. X is to Y is 2:3. So that should be written as X by 2 is equal to Y by 3, and not as, this is the wrong way of writing, X by Y is 2 by 3. Though people will say these two are one and the same, you know, this X, take this 2 down and take this Y up, you will get X by 2 is equal to Y by 3. Still, this is the best, this is the perfect way of writing it. Yeah, so if X is to Y is 2:3, then this is the way of writing. And remember, this is division. X divided by 2 is equal to Y divided by 3. Division just is a simple way of seeing ratios. Ratio doesn't mean it is division. Yeah, be very careful about this statement. Okay, now if this is the case, what if I have X is to Y is to Z is equal to some values A is to B is to C. How do we write this? This will be X by A is equal to Y by B is equal to Z by C. Yeah, so I hope this is very clear. Whenever you have this kind of a ratio, you will write this as X by A equals Y by B equal to Z by C. Okay, so I hope this is perfectly fine. Now let us move to a very important theorem now. This is called theorem on equal ratios. That's a short form of it, theorem on equal ratios. So what does theorem on equal ratios say? Just observe, if I have 1 by 2 and 3 by 6, are these two equal? Yes, they are equal. I mean, this is also 1 by 2. So what I do, if I add the numerators and I add the denominators also, okay, what I have done is I have added the numerators 1 plus 3 divided by 2 plus 6. What does this come out to be? It will be 4 by 8, which is again equal to half. So this new ratio which we have created by adding the numerators of two equal ratios divided by adding the denominators, the ratio which we get is exactly equal to the original ratio. So imagine if this was given to us, if two ratios are given to us which are equal, if we add the numerators, add the denominators, whatever we get new is also equal to the original ratios. What if we subtract 1 minus 3 upon 2 minus 6? This comes out to be minus 2 upon minus 4. So again it is equal to this. So this is also perfect. This both are equal to the original ratios. What if I multiply these two ratios? That is 1 into 3 upon 2 into 6. Just tell me what it comes out to be. This will be 3 by 12, that is 1 by 4. So I am getting this comes out to be 1 by 4, which is not equal to 1 by 2. But if I put a square root, it will be still equal to 1 by 2. That is 1 by 4 will become equal to 1 by 2. Okay, let us try a few more calculations. Now we have done multiplication. Let us divide and see. From here, 1 divided by 3 upon 2 divided by 6. This comes out to be what? 1 by 3 upon 1 by 3, which is equal to 1, which is not equal to the original ratio. So division doesn't work. 1 divided by 3 upon 2 divided by 6 is not equal to the original equal ratios. Yeah, this is very clear. Now let us proceed further, writing some more calculations, like 1 square, this square plus 3 square. So adding squares in the numerators, and then 2 square plus 6 square. What does this come out to be? This comes out to be 1 plus 9 upon 4 plus 36. This becomes 10 by 40, that is 1 by 4. So is 1 by 4 equal to 1 by 2? Yes, provided we put a square root here. So just take a logic which is a bit illogical, that since the degree of this particular expression in the numerator 1 square plus 3 square, degree is 2, you have to put a square root. Yeah, because the square root is nothing but what? Raised to half. So if it's a square, into half becomes 1. Okay. If two numbers are multiplied, 1 into 3, 2 into 6, then degree of this complete term is how much? It's also 2. Hence we put a square root. What if I have 1 cube plus 3 cube upon 2 cube plus 6 cube? Now what we are doing? We are taking cubes of the denominators and adding them, cubes of the numerators and adding them. This will come out to be what? 1 plus 27 upon 8 plus 6 6 are 36, 216, right? This will be 28 upon, this will become 14 to 24. So this will become what? This is 1 by 8. Do you agree with this? Correct? So this is coming out to be 1 by 8. So I have to put here a cube root. Yeah. So I hope things are very clear now, that if you are the degree of the numerators when you are adding or subtracting, if that is cube, then you have to put a cube root. If that is square, then you have to put a square root. Yeah. If suppose I tell you now 1 raised to 4 plus 3 raised to 4 upon 2 raised to 4 plus 6 raised to 4, what will you put here? You will put a fourth root. Yeah. I hope this is very clear. So now if this same thing, imagine if I write this in unknowns, that a by b is equal to c by d, and what is the next term? A plus c upon b plus d, which is just like this, is equal to a minus c upon b minus d, is equal to square root of ac upon bd. So if you just multiply them and multiply the denominator and take a ratio, then you have to put a square root here, and if you add squares, then it is a square plus c square, b square plus d square, and then you have to put a square root, and so on. That will keep on happening. So this theorem, which works always fine, but remember this, both a by b and c by d should not be equal. So here a is not equal to c. That is very clear. Yeah. So from this we state, just have a look at this. I'll give you some time to have a look at this particular terms here. I don't want to rush. So let me proceed. So this is the theorem which we have at hand. This is what we call as theorem on equal ratios. So if a by b is equal to c by d are two equal ratios, then if you add the numerators denominators or multiply, then square root, subtract, and if you take a square, and hence you can create so many of these. So this is given. Without this, if you don't have two ratios which are equal, then you cannot apply theorem on equal ratios. That is obvious, right? Okay. So let me proceed further. So let me solve some problems based upon this particular concept. Let us take this as the first problem using theorem on equal ratios. So here I will show you the K method. Yeah, there are two methods of doing this. You can use theorem on equal ratios also, and you can use the other way around also. Yeah. So what I do is, first let us use the K method. Let x by 1 equals y by 2 equals z by 3. Let this be equal to k. So this implies x will be equal to k, y will be equal to 2k, and z will be equal to 3k. And now I start taking the value of the expression. So expression is equal to x square plus y square plus z square upon xy plus yz plus zx. This will become k square, 4k square, because I am putting y as 2k, plus z is nothing but 3k, so this will become 9k square upon x into y will become k into 2k, that is 2k square, y into z will become 2k into 3k, that is 6k square, and zk will become 3k square. So finally when I simplify, I get 9 plus 1 10, 10 plus 1 14k square divided by 8, 9, 10, 11k square. This will become 14 by 11. So the value of the expression is coming out to be 14 by 11. Now this was K method. Now let us see theorem on equal ratios, how it's going to help us solve the same problem in a different way. So here I have x by 1 equals y by 2 equals z by 3. What I do is I write x square plus y square plus z square, which I want to produce here, upon this will become 1 square plus 2 square plus 3 square, thanks to theorem on equal ratios. But since I want to keep this ratios equal, I have to put a square root because I have taken a square here. Yeah. So this is what we get. Next, again I can say that xy plus yz plus zx. If I do this ratio, product and then sum, I'll get this as 1 into 2 plus 2 into 3 plus 3 into 1. This will fetch me with the square root, of course, because the degree is 2 here, x raised to 1, y raised to 1, degree is 2, so I have to put a square root. Now comparing this expression with this expression, I get next step, which is x square plus y square plus z square upon 1 square plus 2 square plus 3 square is equal to xy plus yz plus zx upon, this will become 2 plus 6 plus 3. So finally I get x square plus y square plus z square upon, this will become 14, 9 plus 4 plus 1 is equal to xy plus yz plus zx upon, this will become 9, 10, 11. So this gives me x square plus y square plus z square, cross multiply, I'll get xy plus yz plus zx is equal to 14 by 11. So by the same method we have got the same answer with a different method. Yeah. So this was about theorem on equal ratios. We'll take another problem. In the meantime, you can pause the video and copy the solution. This is the next problem. So if a square plus b square is equal to 1, where a, b belongs to real, then prove this. Now this is not an easy problem. Yeah. This is the last problem which we are discussing in this whole discussion of ratio. We'll carry the next part in the next lecture. So here if you see, I want to prove this. Squaring, taking a cube over this expression might be a very tedious task. So here comes theorem on equal ratios to help us to solve such a complicated problem, and that is how you will realize that theorem on equal ratios is a very, very powerful tool. So let us solve this problem. I have the left hand side and the right hand side equal, but this is something which is given, so always remember, you should never forget the given. Moreover, what other observation I have? If you see here, this 1 minus a, b, 1 plus a, b terms are visible, 1 minus a, 1 plus a. So the best thing to do is, given, whatever is given to us, let us try to write it in such a way that it gets us, or rather helps us to solve the problem. So I'll write b square is equal to 1 minus a square. That implies b square is equal to 1 minus a into 1 plus a. And if I write this such that you can see everywhere in this prove that I have 1 minus a in the numerator and 1 plus a in the denominator. So I'll get 1 minus a upon b. I take 1 plus a below. If I write like this, 1 minus a, 1 plus a will take below and b will take below here. So b, 1b is left here and 1 plus a. So if you cross multiply this, this is what we get here. You can realize that, correct? Okay. So with this two ratios equal, remember, do you remember that you can apply theorem on equal ratio only if you have two equal ratios? Yeah. So we start with this. We have 1 minus a upon b is equal to b upon 1 plus a. Now we have arranged the ratios in such a way that 1 minus a is in the numerator and 1 plus a is in the denominator. Yeah. Now the next step will be, we want cubes here. Can you see everywhere b has a cube, 1 plus a has a cube, 1 minus a has a cube. So I can say that at this stage we cube on both sides. So after that we get 1 minus a the whole cube upon b cube equals b cube upon 1 plus a the whole cube. Yeah. Now what I do, I say that, let me take these ratios together in the next line. Yeah, here, and now start solving this. So this will be equal to, by theorem on equal ratios, I add the numerator. So can I say this is exactly, a replica of, let me call this expression as capital A, this expression as capital B, this expression as capital C, that is B cube is capital C, and 1 plus A the whole cube is D. So this will be equal to A plus C upon B plus D. Yeah. So what do I get here? 1 minus A the whole cube plus B cube upon B cube plus 1 plus A the whole cube. That's fine. Yeah. So you can see that I am successful in creating this expression here, this complete expression I have created, but without this square. This is not there. Yeah. Now this I have created. So this much part of the expression is been created by me. Square is still left out. Now what I do? You can see that I want 1 minus A and 1 plus A. 1 minus A and 1 plus A. So what I do? I call this as AC upon BD. I multiply the ratios, the numerators and denominators, and then I have to put a square root, right? Because degree is increased. If you remember theorem on equal ratios. So by this what I get? AC. AC is nothing but what here? AC is A 1 minus A the whole cube B cube upon B cube into 1 plus A the whole cube. So B cube gets cancelled. I get square root of 1 minus A the whole cube upon 1 plus A the whole cube. Now what I do? I compare this to, this expression is ready. This is equal to this ratios, and even this is equal to this ratio. So can I say these two are equal? Yeah, but this square root is not there here. There is no square root here, that's missing. So what I do? I square on both sides. So as soon as I square on both sides, what do I get? I get this will be equal to 1 minus A the whole cube plus B cube from here upon 1 plus A the whole cube plus B cube, and then I have squared on both sides, so I get a square which gets rid of this square root. I get 1 minus A upon 1 plus A the whole cube, because this cube is there, so I can write it common. So this is how we have got the solution to the problem. So can you imagine the kind of toughness which this problem was carrying is been very easily solved using theorem on equal ratios. So please remember that theorem on equal ratios might look very obvious, but it's a very important concept. Yeah. So here we end this lecture. That's a lecture which comprises of indices and ratios. Yeah. Just observe this solution and copy the solution. Yeah. See you for the next lecture. You can just pause it as of now and take down the solution. Thank you.